In this video, I'm going to introduce the topic of ionization energy. I hope you like the video, hope you find it helpful, and if you haven't already subscribed to the channel, I'd love you to do so. So the first thing we need to talk about is what is ionization energy. So that's defined as the energy needed to remove a mole of electrons from a mole of gaseous species. And species, as you'll see, can be atoms or ions. So why is energy needed? Well, the electrons experience electrostatic attraction from the protons in the nucleus. So obviously we've got to put energy in to overcome that. And the other thing we'll talk about on this slide is what are the factors affecting the ionization energy. So the first one is the nuclear charge, so how many protons are in the nucleus. Next one is the atomic or ionic radius, depending on what kind of species you've got. If you've got an atom, it's atomic radius. If it's an ion, it's ionic radius. So that's the physical distance between the nucleus and the electron that's being removed. And the other factor is electron shielding. So any inner shells that you've got between the electron removed and the nucleus, they're going to create shielding. So they're going to block or reduce the attraction between the protons in the nucleus and the electron that's being removed. So for the purpose of the video, I'm going to use boron to illustrate ionization energy, and I've chosen that because it's got 5 electrons, so it's only got 5 ionization energies. So it's not going to take us too long to explain everything. Okay, so the first of these is obviously called the first ionization energy, and that's defined as the energy required to remove a mole of electrons from a mole of gaseous atoms. So imagine it's this electron here that we're going to remove. So we'll just take that out. And the equation for the process looks like this. So you can see there you've got a mole of gaseous boron atoms going to a mole of gaseous boron 1 plus ions, and there's that mole of electrons that's been removed. And you can see there the energy that's taken is 801 kilojoules per mole. So removing the next electron is referred to as the second ionization energy. So that's defined as the energy required to remove a mole of electrons from a mole of gaseous 1 plus ions. So we're going to take this electron out. So there's the equation for that process, and there's the ionization energy. That's how much energy it's taken. And you'll notice that it's taken more energy than the first one. We'll look at what the numbers are telling us at the end of the video. But one point I do want to make is I often see an equation like that for something like the second ionization energy. So they've gone from the atom straight to the 2 plus ion by removing 2 moles of electrons. That is wrong. So you've got to do it 1 electron at a time. So removing the next electron is referred to as the third ionization energy. So that's defined as the energy required to remove a mole of electrons from a mole of gaseous 2 plus ions. So we'll take this electron out here. There's the equation for that, and there's the ionization energy value. So you can see it's taken more energy again. And obviously it's the outer electrons that go first because they experience the least amount of attraction from the protons in the nucleus. Okay, so the next electron removed is referred to as the fourth ionization energy. So there's its definition, the energy required to remove a mole of electrons from a mole of gaseous 3 plus ions. So we'll take this electron out here. And there's the equation for that process. And notice the number is significantly greater now. So I will explain that at the end, but have a think about why that number's gone up significantly compared to the previous one. And moving on to the final ionization energy of boron, so that's going to be its fifth ionization energy. So that's defined as the energy required to remove a mole of electrons from a mole of gaseous 4 plus ions. So obviously we're going to get rid of this electron here. There's the equation, and you can see the ionization energy, 32,827 kilojoules per mole. So as promised, we're going to explain what the numbers are telling us. So the first thing we're going to say is successive ionization energies always increase. So successive ionization energy is just the first, then the second, then the third, then the fourth, and so on. So we've got this general increase in ionization energy. So what's causing that? Well, the first thing we can talk about is the charge of the species. So we're starting off with a neutral species as the atom. So we've got 5 electrons, 5 protons in the nucleus, that's neutral. And then we've got 1 plus, then we've got 2 plus, then we've got 3 plus, then we've got 4 plus. So we've got an increasing positive charge of the ion. So any remaining electrons are going to be more strongly attracted to the nucleus each time. The other factor at play is the radius is actually decreasing. So the physical distance between the outer electron and the nucleus is decreasing. So why is that? It's because as the electrons are removed, any remaining electrons are pulled closer to the nucleus because you've got a stronger nuclear attraction for the remaining electrons and they are acting over a shorter distance each time. So that's another factor that increases the ionization energy. Now the other thing we can do with successive ionization energies is actually determine the periodic group from the numbers. So obviously we know that we've got boron here, and these numbers actually tell us that boron is in group 3. So we're looking for that big jump up in ionization energy. So you can see we've got the steady increase for the first, second and third, and then we've got this big jump up, this significant increase in ionization energy going from the third to the fourth. So these numbers are confirming the fact that boron's in group 3, and these 2 electrons here must be in an inner shell because they experience less electron shielding and significantly greater nuclear attraction. Now, as well as a table of numbers like we've got there, we could also be presented with the data in a graph. So this is the graph for the 5 ionization energies of boron. And again, you can see you've got this steady increase for the first 3 ionization energies. So confirmation that we've got 3 electrons in the outer shell, therefore group 3. And then you can see to get the 4th electron out, significantly more energy needed. So therefore, this electron must be in an inner shell. Okay, so we'll just finish with some simple questions just to check everything's made sense. So we've got a table showing the first ionization energies for an element in period 3, and we've got to identify the element. So we're looking for the big jump up in ionization energy, and hopefully you can appreciate that it's between the second and the third. So this element must be in group 2. So which element is in period 3, group 2? It's magnesium. Next question, how many ionization energies does magnesium have? Well, we've got 8 in the table, but it's got 12 electrons, so it's got 12 ionization energies. And the final question, write the equation for the 8th ionization energy for magnesium, include state symbols. So we're going to go from the 7 plus ion to the 8 plus ion. We're not going from the atom straight to the 8 plus. So 7 plus to 8 plus, and remember it's always gaseous, so the state symbol can only be G.